Okay, in this video we're going to try to explain some of these four properties, or all of these four properties that are characteristic of metals. We're representing our structure of our metals with our cations being the red and the valence electrons being the black magnets. The first one we're going to look at is the high melting point. The relationship between each of these cations and the sea of valence electrons is an electric attraction, so it's very, very strong. It's non-directional, but it's strong. Because it is a strong bond, the melting point is from quite high to very high. So they have high melting points because the amount of energy required to break those bonds is very high. That's what melting point actually tells us. The more energy required to break a bond, the stronger that bond is. So if you were given 2 or 3 different metals with their melting points, the one with the highest melting point has the strongest metallic bonding in it. The one with the lowest, like for example mercury, where it's a liquid at room temperature, the one with the lowest melting point would have the weakest metallic bonding in it. And that can be for a variety of reasons: how far apart the cations are to each other, how many valence electrons they have, the density of those atoms. There's a whole lot of factors. But what you need to know for your assessments is that melting point gives an indication of bond strength. If they have high melting points, it means they've got strong bonds. And that is what a metallic bond is. It is strong because it's positives attracted to negatives and vice versa. The second one is about electrical conductivity. The cations can't really move. They're in a 3-dimensional lattice with a certain distance between them at room temperature and so on. When we give an electric force to one side, so plug it into something basically, the electrons can flow, and as they flow, others go with them, and they can pass that energy on, and so they can actually move. So long as they're in a circuit to be replaced by other electrons here, they can carry that charge on to somewhere else. So because the electrons are charged, they're negative, and they are free to move, they're a sea of valence electrons, so they flow like water flows, that means that they can conduct electricity. So because our electrons are charged and can move, metals will conduct electricity. Interestingly, this will also work in its liquid phase. If you were to melt it, a metal still conducts electricity when it's liquid, but then the cations can flow as well, which is pretty cool. But as a solid, which is what we focus on in this standard, the electrons are charged and free to move, so they can conduct electricity. Heat conduction is a little bit different. That's due to vibration of particles that have got a bit more mass. So molecules, atoms, or cations, or anions actually. So because they've got a bit more mass to them. Electrons have got almost no mass. The one electron is 1/2000th of the mass of one proton. So, and each of these are going to have lots of protons in them. So they're way, way lighter, or less dense. So for heat conduction, what would happen if I put a heat source over here is these would start vibrating. So would the electrons, by the way, but that doesn't matter quite so much. These will start vibrating. When they vibrate enough, they will get close enough to repel the next ones, and they'll start vibrating. When they vibrate enough, they do it to the neighbouring ones and so on. And that chain reaction is called heat conduction. Because these cations have a non-directional bond with the sea of electrons, they vibrate a lot more easily than if they were, say, in an ionic bond or a covalent bond. They vibrate a lot more easily. So therefore, they vibrate more easily, and then they can pass that vibration on to the neighbouring cation and so on. So because of its structure being this 3D lattice of cations, and the fact that cations have got a non-directional bond so can vibrate without breaking the bond, they conduct electricity very easily. It is one of the harder ones to explain, so it is one that we should practice. The last one is malleability and ductility. Malleability means I can bend something or reshape it without it breaking. Of course, there's a breaking point to every metal where you do bend it enough that it fractures or breaks. Ductility means I can grab it and I can pull it through a very small circle and it'll become a wire. So it'll maintain its structural integrity at the atomic level, but its shape will change, it'll become a wire. They both work for the same reason. And the reason for that is, again, the non-directional strong bond won't break. So it'll not damage the metal. But it can allow, let's say I was trying to bend this bit of metal, it will allow for the lattice to change its three-dimensional structure and form a new arrangement of particles that is stable. So now I've got our bit of metal bending, can create a new structure because the bonds are strong enough they won't break, but the lattice can be reshaped because the forces are non-directional. So a lot like our conduction, they're able to vibrate without breaking the bond because it's a non-directional bond. We can also reshape it because although it's a strong bond, it's non-directional, so we can reshape that lattice without breaking it. So those are our four key properties of metals that we need to be able to explain. There are others. It doesn't dissolve in water. We'll get to that when we talk about water as a particular piece of learning and things like that. So there are some other properties, but these are the four main ones we need to be able to explain in our assessment work.